So this is another example of solving a system of first-order differential equations. I'm taking this from the context of a population problem, and I'm going to derive the system of first-order equations. You won't have to worry about that, but I just want you to know what's going on in the background. You can look on page 375 in our textbook and find this problem if you want to read more about it. So in this problem, we have two neighboring territories, like two different regions. We'll call one X and one of them Y. And in general, the rate at which a population changes is given by, of course, the derivative. We call P the population. The derivative of P with respect to T is given by the difference between the rate entering the region minus the rate leaving the region. So we have various factors that impact population size. So let's say our region X has a birth rate, we'll call it a little a sub 1. This is just a constant. The birth rate of region Y is B sub 1. We'll have a rate at which citizens of X move to Y. We'll call that A sub 2. And then we'll say the rate at which citizens of Y move to X is this number B sub 2. And we'll disregard the mortality rate. So let's add up the rates that are entering, the numbers entering, and subtract off the numbers that are leaving the region. So for X, that derivative, we have a birth rate. So A sub 1 times X gives us the number growing. We have people leaving X to go to Y, so there's a negative sign there. Plus we have people coming from Y into X, so we'll add that, B sub 2 times Y. And we can simplify that. You factor out an X there, just leaves you with A sub 1 minus A sub 2 times X plus B sub 2 times Y. Now we'll do the same thing for the Y region. So we have a birth rate, so it's B sub 1 times Y. That helps it grow. The numbers leaving, you have to subtract, so it's B sub 2 times Y. And then we have people coming in from X that will add to the population size of Y. So that'll be A sub 2 times X. Again, you can simplify by factoring out the Y there. So this is the system of first order equations. And we can be given some initial conditions as well. An initial population size of X and an initial population size of Y. So that's what these little X's and Y's stand for. They're just population sizes of those two regions. Now we're going to work through an example where we'll have some values for all these constants. And that's what I want you to focus on. Okay, so let's say we have these values for all the constants in that first order system of differential equations, and we have these initial conditions. So when we substitute into the system there, A sub 1 is 2, A sub 2 is 0, and B sub 2 is 3. When we simplify that, we just get 2x plus 3y. A sub 2 is 0, so there's no growth rate. Well, there's no people moving from X to Y, so that's going to impact this population here. So that's a 0. And B sub 1 minus B sub 2 is 2 minus 3. That's also what gives us a negative number. So if you think back, our goal here is to kind of find out what's going on with these population sizes. But if you think back to, like for the first week in class, we looked at some exponential decay problems, and we had that negative sign there. So that's probably that tells us the rate is negative, which means the population size is decreasing. But we'll work through the problem to see it more at the end of the problem. And we are given initial population sizes of 5 and 10. So notice Y starts out bigger than X. So what happens to the population sizes X and Y? Well, let's look at it. So let's write this system in terms of a matrix form. So we just read off the constants, 2, 3. There is no X term, so that's a 0, and Y's coefficient is negative 1. So that's our matrix A. So what are the eigenvalues of A? We subtract lambda from the diagonal. This is an interesting problem. If you've not had linear algebra, this matrix is upper triangular. All the numbers are in the upper part. And it turns out when you find the eigenvalues, you'll just have the product of these two terms minus 0. So the eigenvalues are actually just the numbers on the diagonal. See, you solve that one, set equal to 0, you get 2. Set that one equal to 0, you get -1. So the eigenvalues of either a diagonal matrix, an upper triangular matrix, or a lower triangular matrix are just the elements on the diagonal. These are easy ones to find. Okay, so what happens when we try to find the eigenvector that goes with lambda equals 2? So what happens here, when you put 2 in for lambda, that goes to 0. We already have a 0 here, and this will just give us -3. So we get this system. Now obviously these two rows are constant multiples of one another. I just picked the first row here, so it's 3y sub 1 equals 0. So that means y sub 1 is 0. So here's my vector. X sub 1 can be whatever it wants to be, but y sub 1 has to be 0. Pick x sub 1 to be your favorite number. I'm picking 1, so this gives me my eigenvector. Let's see what happens when we put lambda sub 2 equal to -1 in here. So we get this expression. That should be a -1 there. So we end up with 3, 3, 0, 0. Now, what does that second row tell us? It just says 0 equals 0. So I'm just working with the first equation, which is 3x sub 1 plus 3y sub 1 is 0. That tells you 3y sub 1 is the negative of 3x sub 1. So y sub 1 is the negative of x sub 1. So let's let x sub 1 equal 1. That tells you y sub 1 is -1. So that gives us our eigenvector. And you could have picked your favorite numbers, but whatever you picked, it would just be a constant multiple of this vector that I found. Now let's summarize what we have here. Lambda is 2. There's our eigenvector that goes with it. Lambda equal -1. Here's our eigenvector. So if we put together our solutions, remember the solutions are the vector, eigenvector times e to the eigenvalue times t. So here's our vector v sub 1, e to the 2t. You can multiply it through if you'd like. For the second solution, v sub 2, e to the lambda sub 2t. Here's v sub 2. Lambda sub 2 is -t. So we get this. Now I inadvertently wrote these in the opposite order, but this is your general solution. I actually wrote c sub 2 first, but it's c sub 1 times v sub 1, e to the 2t, plus c sub 2 times v sub 2 e to the -t. So here we have it, c sub 1 e to the 2t plus c sub 2 e to the -t. That's the first component. And then the second component only has this term in it because this term is 0. So you get minus c sub 2 e to the -t. Now, I want you to make sure you understand that the first component here is little x of t. The second component is little y of t. So they're giving us our population sizes. Now, something we haven't been doing is solving an initial value problem, and that's what we're doing here. So let's apply our initial conditions. So this was our general solution. These are our initial conditions. Replace t with 0, so we get c sub 1 e to the 0 plus c sub 2 e to the 0 from this first one. Of course, e to the 0 is just 1, so we get c sub 1 plus c sub 2 is 5, because x sub 0 is 5. Plug it in here, y of 0, we get minus c sub 2, e to the 0. E to the 0 is 1, so that all this is just equal to 10, minus c sub 2 equals 10, so c sub 2 is -10. Now, you know c sub 2. You can go back to the other equation. C sub 1 is 5 minus c sub 2, so substitute that in. You get 15 for c sub 1. So here was our general solution. Replace c sub 1 with 15. Replace c sub 2 with -10. Here was the second component. Replace c sub 2 with -10, so the negative of -10 is 10. So these are our solutions. So you have little x and little y. So what happens to these population sizes? Remember early on we said that derivative of y was negative, which indicated that the population size was decreasing. And sure enough, that's what's going to happen. If you look at x, let's look at the limit. as t approaches infinity for x. Here's our function. Now the e to the negative t part, that's going to 0, but e to the 2t is going to go off to positive infinity. So this x is going to go off to positive infinity. So it's growing exponentially, and will go off to infinity. For y, here's the solution, 10 e to the minus t. That part's going to 0, so the whole thing goes to 0. So it decays exponentially to 0. So in this population problem, the x population grows to infinity while the y of t population decays to 0. So that's just an interesting application. But the important thing for you to be able to do is find the eigenvalues, eigenvectors, put together the solution, and you could apply the initial conditions. I just wanted you to see how to do that.